Well, good morning, everyone. This is the final haul here we're on, or the final trawl. Sorry. The blog is due today at 11:59. That's me out there, I think, on the boat, and TJ's out there somewhere. Peter. Anyway, the blog's due tonight, 11:59. Please submit it. Just get it done, get it in. If you don't get it in tonight, you still have till Friday at the very latest. After Friday, I'm not going to take anything because we got to pound out the grades and whatnot. Yes.
Just to confirm, it's just one document for a group, correct?
That's right. Yeah, just one. You can do a group submission for all of you. But there's two documents, right? There's the one with track changes, and then there's the one that's the final document that you'd like to see published on the water blog. I can't do office hours this afternoon, but I will do them tomorrow from 10 a.m. to 12 noon, and they'll be virtual. They'll be, yes. Oh, that's a good, yeah. Yeah, that's fine. You can submit a Google Doc or a Word document. That's best. You know, I suggest doing a Word over a PDF actually, because if we want to publish it and we have changes or edits to make, it'll be easier to do it that way. But we'll take it any old way. I'm not going to be too hung up on that. I think some of you asked if you could have 1,500 words or you could have more than 1,000 words, and yes, that is okay to go over 1,000, but don't go over 1,500. Period. It's too much. Okay. So office hours tomorrow, last day is Friday, and I just wanted to invite everyone. I mean, you all are here and have been coming pretty consistently. I can tell by squinting at the audience, but those of you who have not been coming in, Friday might be a nice time to come in. We'll do a poetry slam with the finalists from the poetry submission, which are pretty good. We'll have a small award ceremony, and then there'll be a short lecture to kind of wrap up with, and that'll be it. And then of course there'll be the final exam, which can be in person or remote. So I wanted to kind of wrap up the whole fish talks I had with the final little bit here. You know, the post Renaissance movement. You know, the Renaissance kind of recultivated this new materials and new ideas about science and art and classicism, and people learned to, you know, render things with newly found detail and specificity. So these are herring. You can tell it clearly. Samuel Marsden Brooks is actually well represented in California. He's an eccentric California artist, I believe, lived in San Francisco. Here's another one by Brooks. You can tell what these are, right? There's a diagnostic character just jumping out at you there. What are the big fish? And how can you tell? Adipose fin, yeah. And it looks like there was some jack smelt. But post, you know, that was the sort of Renaissance. He was like the later extension of the Renaissance, this kind of accuracy and detail. But then the modernists came onto the scene in the late 1800s and 1900s, and these included the Impressionists, which were really interested not just in the subject, which had been, you know, the subject, by the way, had become the object, and the object had become the thing of desire. And there was sort of this commodification because you could own the thing that you were painting. And then somebody realized, or people realized, that, you know, it's not just about representing the thing and being, you know, showing your wealth that way, but actually you could just possess the art piece, and that had value intrinsically. And so people moved away from this idea of painting things to the actual painting itself becoming a thing. And so the Impressionists grew out of that idea, either explicitly or implicitly, by playing with color and light and shape in ways that pulled them back from the detail of the objects themselves. This is a picture by Renoir, famous Impressionist, and he's not very concerned with the details. You know, you can't really tell what the fish in the basket are. He's concerned with the movement of color and the movement of shape. This was a Russian expressionist or impressionist / expressionist who essentially did this still life with rayfish after an earlier painting, which was in the sort of Renaissance tradition of specificity. And he used the ray as this kind of opportunity for abstractionism, as well as the manipulating color. He didn't care if you could tell it was a ray or not. He was riffing off of Chardin's earlier painting from the 1700s. Here's another Renoir, still life with fish. I can't really tell what the fish are. Maybe they're herring, popular fish in Europe, but otherwise it's unimportant. And then, this idea became even more abstracted so that, I don't know, can you tell who this is? Yeah, it's Van Gogh. It's Van Gogh. So Van Gogh, like, took the idea of expressionism or impressionism to this expressionistic frenzy of color and light. You've all seen Starry Night. And here's his starry fish. Here's a fish on paper. And, you can't identify the fish, but there's some details that really caught his eye, like the scales maybe on the lateral line or on the underside, he gave them this kind of luminescence, because that's what he was interested in. And then a later movement developed, sort of a further extension of modernism, or what became the sort of true first step in modern art. This is by Georges Braque. You might have seen like Nude Descending the Staircase, which is this cubist portrayal of a figure going down a staircase. It's really strange. It's done in these blocks. And the idea is that he's taking multiple images and or multiple perspectives and trying to flatten them into a canvas. And so here, this has actually been determined to be a cod. And maybe you can see it. It's right here is the head of the cod and the fin. But what he's doing, you can also see a side view here. With the cubists, they were trying to take multiple perspectives and unfold them like a piece onto like an origami, flattening out into a flat piece of paper again. And that was what they were playing with. And then Picasso grew out of that movement and incorporated new features, and especially African art and masks and cubist ideas. Paul Klee pulled it even further so that doodles became artistic. And here the idea of a fish is it's just a fish. It's not a thing worthy of noting. It's not interesting to them. And it's ironic to me, and this is Salvador Dali with the same kind of thing. It's ironic because, as you can, or maybe not ironic is not the word, but you can see there's been these shifts in painting fish and other objects, like going from extreme specificity to very much an abstraction to back to specificity. And the modernists were, really back to, in a way, the modernists and the postmodernists became really interested in less the object and more the action of painting. In a weird tradition, it's like kind of like the medieval painters were really interested in this abstract notion of God and Christianity more than the thing they were painting itself. And so then we come into the postmodernist movement, which we're in right now, and people are finding new ways of sort of returning back to, there's many different forks in the art movement right now today, in the postmodern period, I guess you would call it, or the contemporary art. Representation as portrayed through the eyes of different cultures in different places in the country and throughout the world have taken precedence with a new emphasis on rendering detail. Here's another example of that from the Japanese, very heavily manga influenced. And here the fish have a lot of specificity to them, but they're also very, they're abstract in terms of, it's almost like a bestiary. These are, the whole manga tradition is sort of this kind of, it's an abstraction of reality into like new extremes. And so this is, you hear someone's doing it, Haikala is doing it as like high art. And then, the whole internet has provided different opportunities on the long tail of the marketplace for artists who do traditional things like stained glass to incorporate modern themes of science. This is a food chain piece that I think was advertised on Etsy, or actually, I guess it was Google. This is a glass artist specializing in science art. And that's just something that's a function of the new means of communication, right? And then there's something which we didn't do this quarter called Sunday Fish Sketch, which is hashtag Sunday Fish Sketch, which is something on Twitter where people do take time out just to draw, just to render, and then they post it and share it. And there's a kind of, Andrew Ripple had people contribute to that last year, I think, for extra credit. We didn't do that. Anyway, that's it for art. Now you know everything you need to know about art history and fish, or at least a small slice of it. But let's go back to estimating fishery yields, which is kind of the final lap that we're going to make here. I'm going to talk very lightly on this, but hopefully we'll do a enough of a deep dive to kind of get your teeth into it. The main question that we had is, what do you need to evaluate the status of a fish population? And there's a couple of different populations that we have to think about. There's closed populations, like you would have in a lake or a pond, which are relatively easy to assess. And there's open populations, like pelagic fish populations in the open ocean, which are very, very hard. They present a different set of challenges to estimate them. But in general, the key metrics that we need for a really precise estimation of a fishery is to know, these four things we talked about: the growth and rate, age of maturity, fecundity, larval survivorship, and then being able to know the number of recruits and the size of your stock. And it's that last piece that's particularly important, because you can't always get all this information. But that last piece is really crucial to making any kind of estimate to evaluate the scope of your fishery. And I can say that for most of the history of fisheries, we've done this wrong, or we've poorly estimated it. And we've made some incorrect assumptions as well that we may have come a little bit further in rectifying in the last 20 or 30 years here. So sampling fishes is like, obviously this is really key to that fourth pillar of evaluating fisheries. And is my dog still here? Is he? Oh, there he is in front of me. Okay, sorry. Fisheries, and this is a key difference between sampling fishes for science and sampling fishes for profit. In the fisheries industry, fisheries are trying to maximize their catch by using technology to target their catch. And they use sonar, spotting planes, radio. They go in and they hone in based upon conditions and experience where they think the most fish are going to be. And scientists don't necessarily want to target the population, because what if you have a giant lake and the fish are just distributed along the edge? Then fishers are going to fish. They want to maximize their catch per effort. They're just going to fish the edge, right? But it doesn't, if you're going to calculate the number of fish by volume or surface area of the lake, it's not a very effective strategy. It's going to give you a highly inflated number. It makes it easy to overestimate how many fish you have. If you're a scientist, you would want to go in and randomly sample across the lake. You might want to give a little, you would want to, just to make it simple, you might want to put some more emphasis on where the fish actually are. But you have to be able to randomly sample where the fish aren't. And in this scenario, 0, you hear scientists say this a lot, 0 is a data point in ecology. So where the fish aren't is as important as where they are, just because it tells you something about the life history of the fish. And it also evens out your catch estimate so that you have a much less high, you'd have a lower number if you were sampling in the middle of the lake where the fish aren't, as opposed to just, as well as on the edge, as opposed to just sampling on the edge. And this is the central conflict, because in the open ocean, most of our data on fisheries populations in the open ocean come from fishers themselves. And so the question becomes, okay, how do we scale this properly to avoid overestimating? I'll give you an example of why this is a problem in a little bit. Another issue is how you're going to sample a population can also really influence it. In a marine system, like off the coast of California, it's this really, really rocky, ragged environment. And for this reason, there are some people who say that when we declared a decline in rockfish, it was because we were just undersampling the population. And it could be that one of the reasons that the rockfish population rebounded in 10 years instead of 50 or 100 that was expected to take is because the rockfish were hiding down here in the crevices and caves. And as soon as fishing pressure was released, they moved back up into the more exposed areas. And so our catch changed. Now, working with fishers, there's a more elaborate system of evaluating the nature of the population, using a lot of rod and reel sampling of all things to more accurately get a representation. The truth is, we'll probably never really know for sure, but that is what the status of the population was in 1990. But we can say that at least part of the population was overfished, and we just don't know about the rest of the population that might have been taking a refuge, essentially an unsampled refuge below. Yeah. Yeah, they were relying almost exclusively on fish catch. And so then they partnered up with fishers who were unemployed at the time. This is in the 2000s. Yeah, it would have been in the late 2000s. They started partnering up because these guys were out of work, right? So they wanted to put these angry fishermen to work who were putting a lot of pressure on the Fisheries Commission to open up the fishery. They were claiming that, well, in reality, the fish wasn't, the population wasn't collapsing, that it was just a matter of sampling. And so scientists and fishers working together. I showed a little video on that, I guess a week ago, and that's kind of that process that they described, this collaborative process. And I think it was very, very useful. I think that it's still controversial as to whether there was a decline or not. Like I say, there probably was a decline, but it was probably a spatial difference, if that makes sense. So the solution, use different methodologies to validate the numbers. And there's lots of different technologies. We've hit on some of them. You've used some of them. If you went down to Pewter Creek, there's passive gears, which include traps and gill nets and trammel nets, long lines, screw traps. Some of these work better in marine systems. Some work better in freshwater systems. There's also active gear sampling, including midwater trawls and bottom trawls like I run in Sassoon Marsh and seines, which you did on Pewter Creek. There's boat electrofishing and in backpack electrofishing. There's dredging. There's loads of different gears. The problem is that scientists have limited resources to be able to go out. They don't have the aggressive resources that a fishery has. So ultimately, right? Because fishery, to sample, it's one thing to sample freshwater populations where your effort can be constrained in a fairly small area. When you get to marine systems, it gets really weird because it's such a big pool and there's so many different populations, metapopulations and subpopulations that you need to account for. And so we nonetheless rely on fisheries. We have to be able to try to evaluate using the data from fisheries. And that's what the Observer program is about. And I've alluded to this a couple of times. The Observer program has people out there to try to not just measure how many fish, but the amount of effort. This leads to catch per unit of effort. So they essentially, they do an estimate of the volume of water sampled or the number of minutes sampled or the area of water sampled, and they keep track of the space that they were sampling and the depth that they were sampling. And from that, they try to build less an estimate than an index of abundance. The problem is that, again, as I described before, is that fishers are going to move their target always from hotspots or former hotspots where, say, for example, like in this picture up here in the upper right, the red indicates heavily fished areas. So fishers are going to eventually, when competition becomes really extreme in those heavily fished areas, they're going to start moving out. And as they move out, it prevents them from showing a reduced catch, essentially because they're targeting new populations that are outside of the range that they've been typically fishing. And so what the Observer program tries to do is to scale that somehow so we have some sense of whether a population locally is declining or whether the fishers are moving outside of the range. So we use that by tracking boats, their whereabouts, and their effort. So this is the idea of relative abundance in open populations. You use catch per unit effort, and it's just the number of fish you caught per unit of time, per any kind of metric that standardizes it. So it's usually some kind of time or space or volume. So an example here is with the picture that doesn't match. That's random. 125 pollock, which is a marine fishery, per trawl minute. So you'd start counting from the moment the trawl is deployed. You count the number of minutes. If you know the area of the mouth of the trawl, you can then transform that into volume of water sampled, and you can do that volume of water sampled at a certain depth. And it's an effort to try to give you some kind of index. You're never going to be able to get the true population. It's just not available. That's an abstract idea essentially, even though it seems so tangible and so real. You're always talking about scaling it to get some kind of an index. And the reason that we want to do this is because we want to be able to evaluate. Here I use population. It's a theoretical population. Always it's going to be some kind of index. But we want to understand the dynamics of population growth over time. And so we've all heard of exponential growth, essentially a population that's growing without any kind of inhibition. And that's what we see Pull my marker here. So that's what you see in the blue line here. This is an exponential growth curve, which occurs in very rare circumstances or in very short time scales where you have a population that is growing exponentially, essentially without constraint. More typically, we see that there's some kind of carrying capacity in the environment. Carrying capacity in the environment. Carrying capacity can be a hard limit, like the availability of external resources. It could be defined by intraspecific competition. That is, if the fish get too abundant or crowded, they start competing with each other. It could be defined by the space that's available for laying eggs, like salmon creating redds to lay eggs in a river. All those things define this notion of carrying capacity. And it's important to define this, as I'll get to here in a minute. Let me give a few more examples. So human population growth is unfortunately exponential, only in the last probably century, and largely due to the Green Revolution, which produced the first Green Revolution. Wasn't about regreening the planet, it was about food production in the 60s. And then before that, the development of antibiotics has led to exponential growth in the human population. And occasionally in invasive species, you'll also see exponential growth after the introduction. Usually there's a rapid period of growth before they reach their peak. And then once you get an equilibrium population, you've reached some kind of level of carrying capacity here. And this is true of lionfish down in Florida and the Caribbean, when they're Indian Ocean fish that got into the Mediterranean through the Suez Canal and have since been introduced down in the Caribbean. For I don't know, a good 10 or 20 years, we were seeing exponential growth of these fish, and it was really kind of a problem. Now we're providing artificial pressure by essentially trying to hunt them out. They're good to eat as long as you don't get stung by the spines. But more realistically, we have logistic growth, where the population will grow over time and then hit some kind of carrying capacity, usually it's density dependent, not always. But so in the case of paramecium in a lab, once they max out and become so crowded that they can no longer effectively use resources, the population tapers off. And then you get this essentially a logistic growth curve, as opposed to the exponential curve that would keep going. Same thing happens with Daphne in the lab. And then once you start looking at animals in the wild, it's really hard to see this curve. Like sparrows tend to bounce up and down over time. Presumably they hit some kind of, some aspect of carrying capacity, or the environment shifts in such a way, like you go from El Nino to La Nina years, or there's a oscillation in the Pacific decadal oscillation. And so the population is constrained somehow. And so then you'll see these crashes. But if you were to abstract this, you would essentially have like exponential growth. You'd have exponential growth for a period before it flattens out. And then the crash comes when there's some kind of external factor that's moving on these fishes. So, so density dependence usually has something to do with intraspecific competition. And density independence usually has something to do with some kind of outside force, like a change in climate, or a dramatic change in food availability, or a destruction of habitat. Those are all density independent, or largely density independent. And sometimes they're intertwined. So just to help you kind of get the idea, because this notion of density dependence comes in really important. So what would you say? Competition for space, density independent, density dependent? What? It's density dependent. Yeah, absolutely, right? It's competition. I mean, it says it right there. Density dependent. Competition for food, density dependent. Hydrodynamics. It's independent, isn't it? Cannibalism. That's density dependent, yeah. Temperature, independent. Disease. I hear both. So if you have something like coronavirus that emerges out of nowhere, that seems like it's density independent, right? But for known diseases, the fact is that, and you've seen this actually with the coronavirus, it's like intense population hotspots. have tended to get it worse. New York City, parts of Italy, parts of Florida, Southern California, LA. It's a little bit of a density dependent function, right? Disease in wild populations tends to be density dependent, for at least for non-emerging diseases. So you could call this a density dependent factor. How about predation? Density dependent or density independent? Why would it be independent? Anyone? Why would it be dependent? Yeah. That's right. That's right. And predators tend to get a searching image, right? So if there's more if there's more individuals available, predators tend to switch and target on that because they're predators. They're smart. They're designed to hone in on availability of a resource and take advantage of it. So usually predation is density dependent. That's a case of, that's interesting because that's not intraspecific competition, but interspecific competition, which can also be a function of intraspecific competition, I guess. Yes.
What about for a generalist?
Yeah, so generalists will tend to switch towards the resource. So if a prey item has a boom, then those generalists will tend to switch and exploit them, right? So that would be density dependence, essentially. Nutrients, independent, dependent, independent. Pollution. All right, I think you get the idea. I don't need to belabor it. So, based upon that, some people got curious if we could define stock and recruitment relationships based on a density dependent model. And so what they did is they plotted the number of recruits in the y-axis against the number of adults in the x-axis. And the idea is that as the number of, if you could see, or if one could find, how to phrase this, if one is seeing density dependence, you would expect that as the number of adults increases, you would expect to see a decline in the number of recruits. That is, for a while, up until a certain point, which would be that point on the, on this curve here, right? So there's this point where you're having maximum growth. And then there's this point where you reach carrying capacity on the logistic equation, the logistic growth curve. So once you get past this point of maximum growth, the growth of the population should start slowing down. And so this point of maximum growth corresponds to the highest point right here of recruitment relative to the population size. And anything beyond this point where the curve starts to slow down is essentially shows less recruits per number of adults. Does that make any sense at all? I feel like I just like spouted a bunch of garbage at you. Yeah, let's look at another page. So these are for salmonids, right? So in this, the number of spawners, which is the number of adults, is here on the x-axis. And we find that at about 6,000 spawners, we have our maximum number of recruits. That is, the number of babies per adults peaks at that number. And if you increase the number of spawners, then the number of babies you get actually decreases. Why does it decrease? Because there's competition, there's density dependence. When you have a larger and larger population, you're going to have less babies in the following generation because you're competing for space. In this case, it probably is a function of physical space. Salmon and steelhead will come in and they'll wreck each other's redds, essentially laying their own eggs. So if you have too many fish trying to spawn in the same stream, they'll actually start interfering with each other's spawning just by destroying nests. And you'll get a decrease in the population. Make sense? So we saw the same thing with sardines, and people have modeled these in different ways. So the exponential curve is the straight line here, where you would expect that as the adult population grows, you would expect no constraints in that population, and you get this straight line. That's no density dependence. In the case of if there's high density dependence, we get something called a Ricker curve, and that's where the population peaks at a certain number, and then as as the population grows, you get less and less offspring. That's this curve right here. It peaks and then declines. It's called a Ricker curve. And the curve has as an assumption that there's high density dependence. If you model it with just intermediate density dependence, you tend to get a curve that's a bit more like this one here, where the population increases and then flattens out. And then in that case, it doesn't really, you don't see this decline with increasing population. You just see it kind of stabilizes. Well, a lot of people got does that make sense now? Does that help a little bit, kind of? It's a density dependent function. It only happens in density dependent populations. And there's populations with this density independence, that it's the only constraint, then you're going to get a different kind of dynamic. But fisheries biologists thought, woo-hoo, this is a party. That means that if I fish more fish, or fish at the maximum, I can maximize, essentially, if I fish, let's go back to this. So what's the best one? All right, I'll go back here. So, all right. Sorry, I'm trying to figure out which slide is best to explain this. So fisheries biologists got this idea that you could fully fish a population at something called maximum sustainable yield. And maximum sustainable yield is at the peak of the population of this, like say this Ricker curve right here, where there's high density dependence, right here at about 30,000 million tons of spawning stock biomass for sardines would produce the maximum amount of offspring. And that's the place to fish it. And if you underfish it, you're not going to maximize the resource. You won't get as many fish the next year if you underfish it. And if you overfish it, then eventually you'll drive the population down. So this is weird counterintuitive result here, right? More fishing to a point equals more product down the line. And so people got this idea that you shouldn't underfish populations because your industry is not going to be able to survive. You can make a lot more money if you fish right here at the top of the curve to increase your yield and increase your profits. And that's called maximum sustainable yield. I'll get to your question in just a second, I promise. If you're fishing below that, you're not maximizing your profits. If you're fishing above that, you're not maximizing your resource. And you want to get it right at the point in the curve where your production is maximized. Yes. Yeah. Like what if you're fishing a population at its maximum sustainable yield and suddenly you go through like a climatic oscillation that you didn't know anything about? What if some kind of external factor that was non-density dependent shifted in the environment? Either a loss of food because of, say, an El Nino year on the California coast, or pollution, or a predator or disease. Doesn't take into account any of that. Also, it doesn't take into account the basic laws of thermodynamics, which basically say you don't get something for nothing, right? There's always, you've got to be, what you're extracting from the system is going to be a finite amount ultimately. But this came from an era where people thought the ocean was inexhaustible. This was going to feed the world, and the ocean is literally an inexhaustible world. This is before we went to the moon, by the way. This is before scientists went up to the moon and looked back and went, oh my God, it's just a tiny planet. And so once, and we've all sort of grown up with this idea that, yeah, it's a tiny planet with finite resources. And if you exploit the resources at the maximum rate, essentially, you're going to have to pay back at some point. And so your point is well taken. And in fact, it didn't work very well. It didn't take into account density independent factors. And so today in the US, where our fisheries are moderately well managed, some are very well managed and some are still struggling, but we have institutions in place that I think are doing a really good job today of managing resources. But but I think we've had to let go of the precaution of the maximum sustainable yield. And so instead of saying underfish, today we use the precautionary principle. The precautionary principle was developed from the Magnuson Fisheries Act in 1976 and 2006, which kind of was the first federal act, I've spoken about it before, which redefined how we would approach our fishery resources, essentially nationalizing it and taking away some of the power of the individual states to manage fisheries, which they were doing poorly. And so today we talk about maximum sustainable yield, but we have a much more conservative approach. However, in other places, especially on the high seas and other populations or fish populations around the world, fisheries are generally in decline because this idea of carefully managing a population, and essentially you have to combat the pressure to extract more resources for money, and it's an intense pressure. And we have this bureaucratic mechanism set up in the US that I think helps a lot, but in other places, the pressure to fish is really extreme. And just as an example, I sort of talked about some of this, like sardines versus anchovies. So like in Cannery Row, again, a book I recommend you read, it talks about the decline actually it's the characters on Cannery Row in Monterey after the crash of the sardine fishery. And people got the idea that probably the collapse of the sardines was as a function of overfishing, but it was actually both. It was the fact they were fishing at what they thought was maximum sustainable yield. And then there's a shift in the Pacific Decadal Oscillation. And so we went from a cold water to a warm water regime. I feel like I've got that backwards. Yeah, we went from a cold water to a warm water, which favored anchovies. And so the sardine fishery, which had been so profitable, collapsed. And it really got hammered hard. So normally you would expect a shift because they were fishing it so intensively. It's like beating the population when it was down. And this paper by Chavez et al. In Science, they talk about all the factors that lead to this, essentially this anchovy sardine cycle. And in this paper, they were interested in how it affected seabird populations, which were dramatically affected. But the fact is that in general, marine populations are very much in decline. And it's because of increasing pressure. The population of humans has grown by, I think, 4 billion in my lifetime globally. And the pressure to extract resources from the ocean has only increased. And you can see, let's see, I was born in 1961. So you can see that the pressure to fish has increased exponentially. Well, not exponentially, but arithmetically. It's increased steadily since then. And that pressure has led to fisheries moving farther and farther out. So here's an example of one of the difficulties in constraining global fisheries. There's no real authority. And there's pressure once you're in an overfished area to move outside, which both makes it difficult to estimate the population and also makes it easy to overfish a population. So in 1952, this is the Japanese longline fishery, concentrated mostly off the eastern shore of Japan. By 1956, the increasing availability and inexpensiveness of fossil fuels and internal combustion engines led them to expand and population pressure, of course, led them to expand their fishery. And then by 1965, their fishery had essentially expanded all across the world. And even though their catch per unit of effort, remember I was talking about this before, catch per unit of effort was declining, but they were still pulling in the same amount of fish. So, one way to frame catch per unit effort is the amount of time spent on the water, which gives you a more global kind of context, or the amount of carbon spent per fish capture. That would be a way of kind of indexing effort in such a way that you get a kind of general estimation of the decline or the rise or the stability of a population. So we've talked about overfishing. We've talked about fishing down the food web, which is this Daniel Pauly's famous paper about how you remember shifting baselines and how the size of fishes have declined, and also the taxonomy of fishes has declined, such that we're fishing smaller species, moving more towards invertebrates. Fishes that can produce more at a faster rate tend to be smaller, leading ultimately to jellyfish was Daniel Pauly's hypothesis. Bycatch is another problem. So when there's a target fishery and they're catching a whole bunch of other stuff, sometimes the bycatch doesn't get reported. And that can affect things like predators like sharks or marine mammals or turtles, or even like valuable fish that aren't targeted and aren't being listed in the fishery, which is why we have fisheries observers to help us evaluate that. What's my time? How much do I got? Oh, thanks. These are my near frame glasses as opposed to my long. So I got a few minutes. So bycatch has been a major problem. And the fact is, and this is an article that came out in 2006 or 7, where we really finally had to face the fact that oceans really could be running out of fish. This was like a shocking news. And I have to say that the people on this paper are kind of a who's who of fisheries biologists. Boris Worm came out with this idea early in the 2000s, and Ray Hilborn, the second author here, protested loudly, especially about American fisheries. Ray is both a great fisheries biologist as well as a fisheries advocate, a commercial advocate. And so he took issue with some of the analysis, but they came together with these folks. Lotza is on this. Palumbi at Stanford is on this. These are kind of the lions of fisheries biology in the States and in Canada. And they agree that populations are not only overexploited, they tend to be declining. And most of the marine fisheries pressure is concentrated in a few areas up here on the coastal shelves of California and up in the northern Atlantic and along the tropics and here in Southeast Asia and Asia. There's a lot of concentration on equatorial tuna fisheries, on the near industrial population centers for cod and hake, and of course the ground fisheries. And we kind of know what to do at this point. And the problem is incentivizing it. We know that if we regulate fisheries below maximum sustainable yield, we can probably prop them up for a longer period of time. Some fisheries are just too slow growing and we have to halt. For long-lived, slow-growing, low-fecundity fishes, especially like sharks, they're just not sustainable to market, except in little boutique fisheries by hand, maybe. And then, it's really useful to encourage the markets for certain productive fisheries, like anchovy, like salmon. Those are fish with quick turnarounds that are really good to eat and have been sort of neglected, but are very reliable. And then establishing marine reserves, something I wish we had more time to talk about. Marine reserves is very controversial off California, but they're a really effective way of essentially carving out space, especially on reef fishes, for them to reproduce and build up their populations, and also for allow to benthic habitat to grow and become productive, whether it's a kelp ecosystem or a coral reef ecosystem. Large marine reserves with a high degree of connectivity between them, either hydrodynamic connectivity or physical connectivity, are really key to fisheries management. But the problem is just finding the will to do that. And this is easier to do in a wealthy country like our own. It's much harder to do in other developing countries, or countries that are very much bound to seafood that don't have the sort of agricultural wealth that the US has. They're very much tied into the ocean. And so Lou Botsford, who's a very famous fisheries biologist who's here at UC Davis, he retired fairly recently. Lou wrote a very influential paper, a number of influential papers that have been published. And his deal, which I think says it very succinctly, is that the root cause of lack of sustainability is socio-political bias. And that our underlying management failure was that we just had this incessant socio-political pressure to maintain catch at high levels to maximize profits, and that we don't take into account the intrinsic uncertainty that's involved in fishing from a wild population. And so when you fish at the maximum, there's always going to be something that affects you. And so ultimately, we can create, if we follow this advice, we can create a more stable living for fisheries resource jobs while not imperiling the population by managing them at a more sustainable rate. And I showed a plot, I don't know, a few lectures ago, where I showed the size of the ground fishery and how it contracted over time. It was really, for a while in the 80s, it was like a free for all. Everyone with a boat was like, I'll get rich. And then finally, with constraints, that population of fishers, excuse me, the size of the fishing industry contracted, and now it's much more manageable as a result. And that's just a key thing, is having enough muscle to reduce it. So to reduce fishing pressure. So I'm going to kind of wrap here with I guess got a few more minutes, but my next few minutes, and then the lecture on Friday will talk about change and fish conservation. And there's 6 major drivers that I think we have to account for, both in freshwater and in marine systems. This is my general hypothesis here, is that we have to deal with habitat loss, both in the marine and freshwater systems. Climate change, of course, is everything, right? Climate change is really imperiling every aspect of how we manage fisheries and our lives. Invasive species are a huge problem for fishes. Water scarcity is tied to climate change, but not exclusively. A lot of water scarcity is produced by human decisions. And then overfishing and pollution. These are the 6 kind of pillars of managing biodiversity in the future. And just so we can think about this for next time, in North America, we've got about 1,000 freshwater fish species, of which 35% need protection. And you can see the number of extinctions here on this graph shows the rate of extinctions in North America. In Europe, there's many less sort of species diversity in Europe, but about 40% of those need protection. In Australia, 200 species, and 15 to 30% are in trouble. And in South Africa, there's about 100 species and about 60% are. So these are the general populations. These are countries with a highly developed scientific research base, and so they have some sense of what the imperilment is. But we don't know much about Asia, North Africa, and South America. But we can assume that the numbers are really similar. And the next lecture, I want to talk about each individual aspects of these, and what we can do as biologists to try to turn this around, why we should think it's important. Thanks, everyone.